75.6 kilojoule per kg. So you are supposed to calculate the flow rate of the product. So just try to understand how these questions have been, you will be able to solve this particular problem. So let's say if you have one is super saturated stream having molar flow mass flow rate is 600 kg per hour, that is given to you, and another one is a superheated stream, and the enthalpy here is also given, that is 2675.4 kilojoule per kg, and the this one. So let's say I'm assuming the mass flow rate F1 is this one, and here this one is F2, right? So here enthalpy is also given, and enthalpy here is 3382.4 kilojoule per kg, and after that you are getting a superheated product, and I'm assuming the superheated product molar flow rate is your, let's say, F3, and the enthalpy here is how much, 3175.6 kilojoule per kg. So you are supposed to calculate the flow rate of product stream, that is F3, right? So just try to understand one thing. So here this question is based on two things. First is you have to apply the material balance as well as the energy balance. So if we apply material balance, so first how will we solve this particular problem? So applying so if you apply material balance, what you can write, F1 plus F2, that is equals to F3. So F1 is your 600, that is equals to, sorry, plus F2, that is equals to F3. So this one is your equation first, right? And next one is that second one is your energy balance, enthalpy balance. So if we want to apply the enthalpy balance, so what we can write, F1 multiplied with energy by H1 plus F2 multiplied with H2, that is equals to F3 multiplied with H3. So here you can see enthalpy of all of these streams have been given to you. That's why I'm directly using F1 into H1 plus F2 into H2 is equals to F3 into H3. There may be a case where they will be giving you the CP of all of these the flow stream, and based on the CP you have to apply H is equals to CP delta T, something like that. So I'll tell you the case there. So what is F1? F1 is 600 multiplied with, and H1 is given 2675.4. So you can write 267.75.4 plus, again the thing is that you can see the enthalpy unit are same for all the stream. That's why there is no any confusion about these things, but it may be possible that they can change the units of enthalpy, so you have to take care of that thing also. So again you can write F2 multiplied with, again, 3382.4, that is equals to, again, F3 multiplied with 3175.6. so this one is our equation second. So now you can see you have two unknown and two equations, so you can very easily solve this particular thing. So let's say here 600 multiplied with 2675.4, but you are supposed to calculate the product stream. So I'll be making this equation in terms of variable F3. So what is F2? F2 will be equals to here F3 minus 600, and again you can multiply this 3382.4, that is equals to F3 multiplied with 3175.6. So now this is very simple equation now, so you can solve these things very easily. 600 into 2675.4 minus 600 multiplied with 3382.4, that is equals to, if I'll take common F3, so that will be equals to 317.5 minus 600 multiplied with 3382.4. So once you will solve these things, you will be getting the value of F3, and I think you will get the value of F3 is 2051.257 kilogram per hour. So again, at the end of once you are able to solve the question completely, just check the unit once. So it may be possible, if they are not going to change the units in the problem, then definitely it may be possible that they will change the units in the solution or options also. So you have to take care of this thing, right? So this is how we can solve the energy balance problem. Okay, now after that I'm moving towards the next problem, that is based on the recycle stream. So here you can see this problem says the carbon black is produced by decomposition of methane, that is CH4 in the gaseous stage is getting converted into carbon in solid plus 2H2. So this reaction is happening in the reactor. So let's try to understand how this thing is happening. So you are having a reactor and the reactant is entering and the product is coming out, okay, and your CH4 is your reactant and the product is obviously your some amount of CH4 may be there. If complete conversion is not there, carbon solid will be there, and again hydrogen in the gaseous state is there. Single pass conversion of methane is 60%. So here you can see the single pass conversion is given, and if fresh feed is pure methane, so here this is pure methane only, pure methane, and 25% of methane exiting the reactor is recycled. So let's say how much methane is getting recycled here. So the amount of, let's say I'm assuming here this is 0.1, this is your 0.2, and this one is your 0.3. Is that clear? So let's say number of moles of methane at 0.3 here, CH4, whatever the number, 25% of methane exiting the reactor is recycled. So how much it will be there? 0.25 multiplied with n number of moles of methane at 0.3, something like that. Okay. And the single pass conversion is given also 60%. So what is single pass conversion? So if number of moles of methane here, let's say I am assuming CH4 at 0.2, and here if I am assuming number of moles of CH4 at 3, so what is single pass conversion? So number of moles of CH4 at 0.3, that will be equals to number of moles of CH4 at 0.2 multiplied with how much? 1 minus since 0.60. Is that clear? So that will be equals to 0.4 multiplied with number of moles of CH4 at 0.2 at number of moles of CH4 at 0.3. So this one is the case. So if you are solving this kind of problem in this way, then definitely there is less chance of doing any kind of silly mistakes over there, right? After that, you are supposed to calculate mole ratio of fresh feed stream to the recycle stream. So let's say if I am assuming fresh feed stream is 100. Is that clear? Fresh feed stream is 100 only, and here single pass conversion obviously you get to know. So now what will I do? So see how again, yeah. One more thing is that, so what is number of moles of methane at 0.2? So number of moles of methane CH4 at 0.2, that can be written as 100 plus number of moles which is coming from the recycle stream. So that is equals to 0.25 multiplied with number of moles of CH3 at 0.3. Is that clear? So now you can substitute any value here. So let's say if I am substituting this value here only, right? So what I can get, so number of moles of methane at 0.2, that will be equals to 100 plus 0.25 multiplied with 0.4 multiplied with number of moles of methane at 0.2. So from this particular equation you can get number of moles of methane at 0.2 into 1 minus 0.25 multiplied with 0.4, that is equals to 100. So you can get number of moles of methane at 0.2, that is equals to, what is 1 minus 0.4, so that is equals to 0.1. Is that clear? Multiplied with, sorry, this is just a simple calculation now. So that will be equals to 100 divided by 0.1, so that is equals to 1000. Sorry, this will be 100 divided by 1 minus 0.1, so 0.9, so that is equals to 1000 by 9. Is that clear? So now you get to know that number of moles of CH2 at this point, at 2. So based on this you can get number of moles of CH3, sorry, number of moles of CH4 at 0.3, that is equals to how much? 0.4 multiplied with 1000 divided by 9, that is equals to 400 divided by 9. Now what is recycle stream? Now recycle stream is this one only, so that is equals to 0.25 multiplied with 400 divided by 9. So you can write 25 by 100 multiplied with 400 divided by 9. Is that clear? So that is equals to 100 by 9. So what is you are supposed to calculate some ratio here, right? So you are feed by R, fresh feed divided by recycle ratio, that is equals to 100 divided by 100 divided by 9. So here you will get the answer is your 9. So the ratio of fresh feed divided by